Hey all, welcome to the 7th session of my lecture on architecture and programming models for GPUs and coprocessors. And we're currently talking about computer graphics and rendering algorithms, and last time was our first session to start our discussion on that. And we started our discussion with a review of the light transport equation, and we learned that this is the governing equation to computer graphics. And we also learned about triangles and triangle meshes, and that they are like the base primitive for computer graphics. And right now we're trying to figure out how to actually turn triangles into raster images. And the process here is called scan conversion, and is basically the primitive operation for the rasterization algorithm. And we started our discussion based off of the idea that we first just take the triangle edges and then scan convert those triangle edges, and then later fill in the pixels in between with appropriate colors. And therefore we discussed this family of algorithms, like where DDA or Bresenham belong in, and those are basically based on inspecting the slope of the triangle edge and then making an iterative decision if they just go to the right, or if they go to the right and also go up, like we had inherently iterative approaches. And today I'm presenting you an algorithm that is doing slightly better in that it is not that iterative, but it is easier to parallel. And this algorithm is called the algorithm by Pineda, who presented it in 1988 at SIGGRAPH. And the idea of the algorithm is that the triangle edges subdivide the 2D plane into negative and positive half spaces, and based on the half space that we're in, we can also determine if we're inside a triangle or not. Like, I'll give you a very quick overview of how the algorithm works conceptually. And then later we will discuss it in a bit more detail, only to defer a very detailed discussion to the exercises where we'll actually formally derive some of the equations that are important to the algorithm. The basic idea is that in order to scan convert a triangle, we first compute its axis-aligned bounding box. We take its 3 vertices, v1, v2, v3, and we're now in window coordinates. And window coordinates implies that we are in 2D, right? We are in 2D, and each of those v1, v2, v3 has a depth associated with it, and this depth is just an attribute of the vertex. So this is something that computer graphics people colloquially refer to as 2.5D data. We have a 2D coordinate system, and then we have this depth coordinate, which is like there's a bunch of different attributes associated with the vertices, like for instance normals, but also depth. Depth is kind of important because depth is later used for the visibility decision. And therefore, we refer to the type of data that we have here as so-called 2.5D data to signify that depth is important. But still, our coordinate system is in 2D, so we compute a bounding box, and this bounding box is actually a 2D bounding box. So this is matter of fact, this is just a rectangle, right? So we compute the bounding rectangle with regards to the 3 vertices v1, v2, and v3. And then we compute edge vectors, like the e1, e2, e3 here. And then we just iterate over the pixel positions x, y in the bounding box. We can do this in parallel, and we can also later see that there's an option to do this iteratively. And then for each x, y, we just solve this equation here, yeah? So we solve the equation, and we'll formally derive the equation during the exercises. I'll provide a bit more intuition in a little bit. And we solve this equation with respect to all 3 edges, this equation here is associated with each of the edges. And we solve it for each of the edges by plugging in x and y, right? And then we determine if the equation evaluates to either 0, and then we know that we are on an edge. And if it is greater 0, then we're inside the triangle, and otherwise we are outside the triangle. And we do this for all 3 edges, and only if for all 3 edges this equation here evaluates to greater than 0, then we know we are inside the triangle. this algorithm actually has a special property. Like when we once computed this edge equation here, yeah, like we computed our EI of x and y, then we can just find out the edge equation for the neighboring pixel positions by performing a simple addition by just adding one of the components of an edge. Yeah. Like this is actually a very useful property. Like it helps us to, like we can now make a decision if we either want to parallelize the algorithm, like we can, for instance, compute all the pixels in parallel, like we just compute the edge equations for all the pixels in parallel, or we do something smarter, like we subdivide the bounding box into tiles, like when we have a large triangle, then we just subdivide it. We subdivide the bounding box into 8 by 8 or 16 by 16 tiles. Like each tile is composed of 8 by 8 raster points or 16 by 16 raster points. And then for each tile, we compute the edge equations in parallel, like we have parallelism over the tiles. And then inside the tile, we use this iterative property here. And this can actually be very helpful because this makes the algorithm very elegant. Like we can actually decide how much parallelism we want and what the costs are. Like when we have more parallelism, we have more floating point operations to perform. And on the other hand, if we decide for the operation with fewer operations, like if we decide that we want to do the iterative thing, this would result in data dependencies, obviously, right? Because when I compute those neighbors here, then I have a data dependency on this already computed edge equation. Yeah, I propose we have a bit of a more detailed look at how that works. Let me just present you a quick example. And for that, we're given a triangle, and rasterization is an object order technique. So we're now going to find out, given the triangle, which raster positions are occupied by that triangle. So the first thing that we note is that the triangle is obviously composed of vertex positions, v2, v1, v3, and then we use those vertex positions to compute edges, right? And what we also can note is that those edges, they prescribe a winding order, right? So the winding order of this triangle here is counterclockwise, right? Because when I follow those edges and with respect to the current viewing position, the edges wind in a counterclockwise order, right? So, and the next thing that I can note, that given this particular choice how I constructed the edges in 2D, and we are now in a 2D space, where the vertices and the fragments and pixels have like attributes, right? And the depth of the triangle at a particular position, at a particular raster position, is just an attribute of that fragment at that position. So we're basically in 2D now, and as we're in 2D, this winding order also gives us a subdivision into half spaces with respect to each edge, right? So like this edge here and the particular choice of how we constructed the edge provides us with two half spaces. Like the half space on the right of that edge here is the negative half space, so to say, and the half space on the left side is the positive half space. And we obviously get that for all the edges. And then you can see that when we're inside that triangle, the area here, when we're inside that area here of the triangle, the union of those half spaces is completely positive, right? So in order to determine which raster positions actually overlap the triangle, the first thing is that you do is you determine which raster positions can actually overlap the triangle. And for that, the first thing is you compute the bounding box of the triangle, and then we found out that only those 16 pixels are potential candidates to actually overlap the triangle. Like we computed an axis-aligned bounding box, and then we found out that all those 16 pixels are inside the axis-aligned bounding box of the triangle. And then we just test for each and every candidate, and we make kind of an arbitrary decision, like when this is not noted otherwise, then we'll just assume that we're performing those computations with respect to the pixel center. This is kind of an arbitrary decision to make, but it's also what people usually do, considering the pixel center, because this later simplifies certain things, like when it comes to anti-aliasing and sampling, etc. So now, in order to find out if the pixel is inside or outside the triangle, we just take each of those edges, and then we determine if our pixel is in the negative or positive half space. Yeah, and we find out that with respect to this edge here, the bottom edge here, we're in the positive half space. And we also find out that with regards to the edge here, we're also in the positive half space, but only with respect to this edge here, we are outside, and this makes our pixel be outside the triangle, right? And I mean, you can imagine how that works. Like for the pixel that is inside, all the edges, or the pixel is inside the positive half spaces with regards to all the edges, right? And so this can be easily used to determine if a pixel is inside or outside the triangle. And you can like do this iteratively or do this for the pixels in parallel. And let's have a look at, let's have an even more detailed look at how that works. Like we will gonna iterate this in the exercises. In the exercises, we also have more formal derivation of how things are working. But here I'm just gonna illustrate what's happening. And what you basically do is you take like you have this triangle, and this triangle prescribes a counterclockwise winding order. And what we do now is we construct triangles of each edge of the original triangle with the pixel. Like I'm doing here. I'm taking this edge, and then I'm constructing another, like an imaginary triangle. And then I'm computing the winding order of this triangle. And I find out this that the winding order is counterclockwise. And this is the same winding order that the original triangle has. And this is good. Like this is what we want to find out. And we will in the exercises learn that the winding order is proportional to the signed area of the triangle. Like you can basically compute the triangle's area. And if the area is negative, then you'll have an opposite winding order to the one that you're interested in, and that will tell you, like in our case, it will tell you that you have a winding order that's clockwise. So, and we found out for this edge here that this imaginary triangle has a counterclockwise winding order, and happens to be the same winding order that the original triangle has, and with that it passes the test, right? And then we go on and do the same test for this edge here, for the edge here down below. And we also find out that the winding order is counterclockwise, like when you just checking the winding order, we do that graphically. And we find out that is just what we want, like the winding order is the same as that of the original triangle. This is good. And then we do this for the remaining edge. And there we can see that we constructed a triangle with a clockwise winding order. And this is the case that breaks it. And this determines that we are in the negative half space with respect to this edge, and therefore the old pixel is outside the triangle. Like when we have, in contrast to that, when we construct the same triangles for this pixel here, like then we find out that all those triangles those imaginary triangles that we construct have a counterclockwise winding order, and therefore we're inside the original triangle. Like there's also a bunch of other tests that we could have done with them with that. Like we can, for instance, also use this kind of test for backface culling and stuff like that. So, and we can now use this in different ways. Like this equation that I showed you earlier on the slide. This is something that that graphics people call the edge equation. Like when I am later referring to the edge equation, or when you see the abbreviation EE, then that means this is an edge equation. And this is basically just this equation here. Yeah. Like we will learn in the exercises, we will learn a bit more about this equation and how it relates to the triangle's area, how it relates to the determinant of a certain matrix. We will learn more stuff about this equation, but when you see this equation and when you hear me calling something an edge equation, I'm referring to this equation, like, and there's 3 edge equations for each triangle, right? And what's really beneficial about those edge equations is that there is 2 ways that we can compute them, right? Like in the when I take the edge equation, then I wanna solve them for x, y, and there's 2 ways I can do that. Like I can do this for just I have those patches, like I have an axis line bounding box or a patch of pixels, and then I can just compute those edge equations in parallel. And this has the advantage of being data parallel. And this is also one of the advantages of the whole method, because this makes things parallelizable. Like I can compute those edge equations in parallel, but on the other hand, I can also compute the edge equation with regards to 1 pixel and then perform interpolation. Like I just compute the value for the single pixel, and then I can just retrieve those other values using a very simple addition. And I have those 2 options. I can actually combine those 2 options. Yeah, like I can, for instance, say compute the edge equation for this pixel here and for that pixel down here, and then perform interpolation for this upper 4x2 tile, and also for that lower 4x2 tile, and I can do that in parallel. And this is actually what makes this approach and those edge equations, and which makes the algorithm by Pineda so elegant. So, and I cannot stress enough that this is actually a very important algorithm, also in regard to potential questions for the exam, for example. We will later work with this algorithm during the exercises and get a more thorough understanding of the algorithm. And then when we have that understanding, we will make use of that understanding when we discuss the GPU rendering pipeline and when we discuss raster engines. So now that we have an understanding of how to scan convert and how to turn triangles and polygons into raster positions, the question remains how to obtain the actual colors that we use for the pixel positions. And the colors in the simplified model that we are using are based off of lighting calculations, and for that lighting calculations we take 2 entities into account. And one entity is the light sources in the scene, and the other entity is the material properties of passive objects that don't emit actual light, but that only reflect light. And let us discuss light sources. Like there are different types of light sources, and one way to model light sources is just to designate some of the objects in the scene, like some of the triangle meshes in the scene, as light emitting. And so in reality, there are certain media, like gaseous media, fire, for example, and those media, they radiate, and they radiate at a certain wavelength, where the radiation is visible as light. So we say those objects emit light. And this can be modeled in different ways. Like one way to model this is just like there's usually a region in space that is occupied by this medium. And the question is really how we model this region in space. And we can just model it with regards to its surface, like we did before with the triangles. And then we can just designate one of the triangle meshes as being representative of that medium. And in certain cases, like we can use even coarser approximations, like when this region of space is relatively small, or when it is far away. In those cases, it is viable to approximate them using so-called point light sources. So we designate an infinitesimal point in space with the light source, and then assign the light source certain quantities that designate it as a light source that can emit light into its environment. And like on the other hand, we can also, like as we know that certain media emit light, we can just model them as that, like as a medium with volumetric properties, where we can just see through certain parts of the medium, and the light emitting property of the medium is maybe varying with space. So we can model this much more complexly. And we'll, in the following, just refer to all those objects that can emit light as light sources. And there are some basic operations that need to be performed for those light sources. it's important when you have a light source that you're able to tell for a certain point in space x. Like you have to be able to tell its light intensity at that point. And then what you also want to be able to do is you want to be able to sample a vector towards the light source. Like consider this medium here that can emit light. Then we have a surface that receives light from that medium. And then the first thing that we do is we perform this approximation where we compute the surface of the light emitting medium. And so we're basically introducing another triangle mesh or another polygonal mesh into the three-dimensional scene. And like in order so that things aren't so complicated, we're not considering that it's a medium anymore. And then what people want to do is when they perform lighting calculations for this point here, they want to be able to sample the surface of that medium. And this is important in cases like, for instance, where you performing like Monte Carlo sampling or something like this, right? Like with that point on the surface, you're able to compute a unit direction vector towards that point. And those unit direction vectors can, for example, be used to compute visibility tests. For example, you can use that visibility direction to determine if the light source is occluded with respect to another object, right? So, and then you can maybe compute another point on the surface and another unit direction vector towards that. And then people use those simple tests to compute the average contribution from the light source. And the average contribution is made up of those direction vectors, like we're sampling the light source. And on the other hand, we're also interested in the intensity at that position. So we have to be able to compute the intensity at a certain position x in space, and we have to be able to sample such a point on the light source, and then we can perform computations like these. And obviously, when we consider the medium as gaseous or as a volume, then things become much more complicated. But when we have those simple like surface or infinitesimal point representations of our light sources, then the basic operations that we want to be able to perform is compute a point towards point on the light source, and compute a direction vector towards the point. Yeah, and I mean, obviously, I also want to show you what this looks like. This is a three-dimensional scene, and the three-dimensional scene is merely lit by three emissive light sources, like this box here, and then this box here in the back, and then this dragon triangle mesh here, and all those meshes. They contribute light, like they are emissive surfaces, and they are triangle meshes with an emissive material property, and that's what that looks like in reality. So in the other entity that contributes to the final pixel color of the scan-converted triangle is the material properties of the objects in the scene. That is the reflective material properties in the scene. Meaning that when we have light that interacts with the material, like we have photons hitting the surface, and then the surface has a certain reflective material property. Those material properties determine how much light is reflected off of the surface. And those computations, like we will motivate this from a physical point of view, and we're assuming that what actually happens is light-matter interaction, like we have particles that interact with each other, photons and electrons, and the computations that we perform are physical computations, and we're assuming that the quantities are radiometric quantities. And when we're talking about colors, like RGB colors or sRGB colors, those are perceived quantities, so-called photometric quantities. Like without going into too much of detail, the photometric quantities depend on things like the brightness of our screen or the brightness of the color that we use for printing a photorealistic image. And the internal computations, they actually don't know anything of photometry and of photometric quantities, and therefore there's a conversion step when it comes to how we store and how we represent physical materials. For that, we will discuss a bit of terminology, and let us consider this very simple scene here. Like we have a scene that is comprised of 3 different surfaces: surface S1, S2, S3, and I will interchangeably sometimes refer to those surfaces as geometries. Like the significance of them is that there is a grouping. Like we have a group of triangles that make up surface number 1, and then there is another group of triangles that make up surface number 2. And then to each of those surfaces, we have certain surface properties. And we're now assuming for simplicity that each of those surface properties can be fully described using one RGB tuple. This is not so realistic. Most materials are more complex, but for simplicity, we're assuming that the properties can be fully described using an RGB tuple. And that allows us to build up something that I will later, that people colloquially refer to as material libraries. We have 3 materials here. We have the material that is assigned to surface 1, and we have the material that is assigned to surface 2, and the material that is assigned to surface 3. Again, if we had more than 3 materials, they could potentially actually share materials. Like we could have a surface S4 here, and it would just reuse the material that is assigned to S1, right? And therefore, we have something that's called a material library. And when we specify those material libraries, we quite often, like this is not a necessity, but we quite often specify the colors. We specify the reflective surface properties as RGB colors. And that basically says when there's light interacting with the surface, it basically tells us how much red, green, and blue light in the color spectrum is reflected. That is, in fact, there is actually associated with the surface property something that we call a spectral power distribution, and it's a spectral power distribution with regards to reflectance, and because of certain properties such as energy conservation, for instance. For reflective materials, those are kept out at 1. The maximum reflectance property is for those normalized spectral power distributions is 1. And then there is a certain conversion from the RGB color that we have to such a spectral power contribution. There are different ways to compute them. And when we have a physically based renderer, those physically based renderers can perform all the computations that are necessary in order to compute those colors based on radiometric quantities and based on those spectral power distributions. This is not a necessity. Many renderers internally operate on RGB tuples. That is, they never perform that conversion. But what is important to keep in mind is that when we perform a physically based calculation, it is just plain wrong to think of the material properties as RGB colors. But rather than that, they're just spectral power distributions, and they tell us for light at a certain wavelength how much light is reflected for that wavelength, right? And we have such a spectral power distribution for each of our materials in the scene. So then, when we perform our computations, we have associated, for instance, we have something like a ray tracer. We will discuss ray tracing later on. But when we compute internally, when we perform the computations in order to determine the pixel color, we're doing this in terms of radians. Many renderers actually approximate that and internally perform the calculations in RGB. But this is an approximation, and it's not fully correct. What you really want to do is perform those operations in terms of radiometry. What you actually compute is you have photons that were emitted from light sources, and they interact with surfaces, and those photons, they influence the internal structure of the material, and then they cause new photons to be emitted, but those photons carry less energy. And you perform this type of computation, and then you carry along with your computation, you carry along radians, right? And then in the end, you end up with a spectral power distribution that is associated with the pixel that you are currently computing a color for. Yeah. So in the end, when you no matter which algorithm you actually used to perform the color computations here, You could have used a ray tracer, or you could have used rasterization. It doesn't really matter. And then in the end, when you have evaluated all those surfaces, and when you also evaluated your light sources, you will end up with a combined spectral power distribution that represents the color of the pixel. And then in order to display the color, you have to turn it into a photometric quantity, like a color, like it would actually be perceived by a human, and maybe a color that takes certain curves with regards to your screen's brightness into account. So you reinterpret that spectral power distribution in terms of photometric quantities, and then you convert it to an RGB tuple. Yeah, you convert it back to an RGB tuple, and then you assign that color. And the motivation here is like you have all those quantities, like you have your colors, and those colors describe what people perceive. Like they describe a color like people perceive the color, like the material is mostly red. And then in order to like be physically correct, like people usually are not physically correct in their renders, but they use approximations. But the ensuing calculations, in order to be physically correct, should be performed in a space that does away with all the perceptual considerations, like converts it to a spectral power distribution, and we can ask that spectral power distribution, like we're currently at a certain wavelength, and at that wavelength, how much light is reflected off of the surface. Like when you have those spectral power distributions, the problem here is that that the sampling rates for those spectral power distributions tend to be quite high. Like when you're in the visible spectrum between 400 and 800 nanometers, you have to use a quite high sampling rate in order to faithfully depict that. And due to certain theory, it's actually kind of okay to actually perform those computations in RGB. Like you can represent a spectral power distribution with an RGB tuple, and you can do that very well, actually. So this is what people do. But internally, what's happening here is really spectral power distributions that tell you for incoming light how much light is reflected off of the surface. And those are the material properties. And then you can also see, you can see that there is an interplay between light and surface properties. Like when there's no light falling on the surface, there's actually also no light that can be reflected off of the surface. And because of that, both the light intensity and the surface properties determine your final output color. So insofar, we discussed those material properties on a theoretical basis, and that we just assume there are surface properties, and that we assume that there are functions that describe how light is reflected off of surfaces. And we also learned earlier that there is something called a BRDF, a bidirectional reflectance distribution function. And we'll now have a look at how those BRDFs actually work, what the constituent components of a BRDF actually are. And materials, depending on their actual properties, can, for instance, be diffuse. And diffuse materials are approximations to so-called subsurface scattering. That is the theory of light penetrating the surfaces and then being scattered underneath the surface and then exiting the surface at a certain and usually not at the exact same position as where the light actually entered the surface. So like we earlier said, that we're assuming that the light cannot actually enter the surface. Like we assume that we're using a simplified model, and the simplified model to this, that is the so-called diffuse lighting model. And as a matter of fact, there are actually different diffuse lighting models out there, and this is the so-called Lambertian diffuse lighting model. The motivation for the Lambertian diffuse lighting model is the following: is just that we have a surface. And the surface is not only defined at the surface itself, but there are also certain properties to the medium underneath the surface. And then we assume that light is being scattered underneath the surface and then eventually exits the surface. And we just approximate that using this diffusion model. So the intuition here is that we have a surface, and the surface bounds a homogeneous medium. That is, the medium underneath the surface doesn't vary in space. and the surface is lit up by a light source, so we know where the direction vector towards the light. And what's happening, and the surface is also translucent. That is, light can potentially penetrate the surface. And what then happens is diffusion inside the medium, right, underneath the surface. Like when the light enters, we assume that light can be scattered into any direction underneath the surface. Like there's equal probability that light is scattered in either of the directions on the hemisphere above the intersection position. And then we assume that light is being scattered. Like we're also assuming that the medium is homogeneous, like those distances should on average be the same. And then we're computing diffusion. That is, we're now assuming we're at a scatter position, and then we again have equal likelihood of the photons that are entered the surface and entered the medium through the surface are scattered in any direction, but now not on the hemisphere, but on the actual sphere inside the medium, like surrounding the scattering position. And then we compute another direction, and we actually computed a bunch of direction, and then due to diffusion, like at some point the photon will somewhere exit the medium, and therefore again penetrate the surface, and then there will be another direction vector associated with this, with another probability that is proportional to the area of the hemisphere, of the unit hemisphere above the intersection point. And this process is called subsurface scattering. And there are actually multiple ways to approximate that, like dipole methods, and you can actually simulate this using Monte Carlo, like the very process I just described could be simulated using Monte Carlo, where you sample distances, etc. This can be arbitrarily complicated, but for a very simple model, like we're assuming we're using a much simpler model than this. We're just assuming that this happens like over and over again. Like we have a bunch of those diffusion processes going on, and then eventually light exiting the surface somewhere. And now the thing is, when we when we move our view so far away from the intersection, from the entry and exit positions, we can assume like the farther we away from that, and the smaller the visual domain of this process actually gets, this distance between the entry position and the exit position will go to zero. And we're making this assumption. We're just making this assumption that underlying our model there is such a diffusion process with a homogeneous medium and equal likelihood of light being scattered into any direction. Like we don't have a so-called anisotropic medium, but we have a diffuse medium. And we then assume that this distance goes to zero. Yeah? Like we're sufficiently far away so that the entry and exit positions appear to be the same. And then it is under those assumptions, it's valid to just approximate the various reflected light directions in a way where we just assume that it is equally likely that the reflected direction is any direction vector above the entry position of the light. Like we assume that entry and exit position are the same, and then we're also assuming that there is a diffusion process with equal probability of direction vectors, and then we can just assume that no matter where the ray enters, the ray will exit at the very same position, and the likelihood that the ray enters into a certain direction is proportional to the area of the unit hemisphere above the exit position. And when we compute this, we just compute this, and we compute the light contribution by just assuming, okay, we're having a hemisphere, and therefore we're just ignoring that whole part that is going on underneath the surface. Like, and when there's a light direction that is underneath the surface, then we'll just assume there is no light contribution. And other than that, the light contribution is just proportional to the angle between the light vector, this vector omega I, or sometimes I might also call that vector L, and the surface normal. And this model is called the Lambertian BRDF. And then there's other surface types that have so-called rough surface properties. And here we assume that the light won't penetrate the surface, so there's no diffusion happening underneath the surface. And those materials are very often like for instance metals or rock or similar materials. And we very briefly discussed this when we talked about the LTE. And those models and those rough surfaces are approximated using so-called microfacet models. And similar to the way we computed the diffusion process, like we approximated the diffusion process with the Lambertian model stochastically, we do the same thing with microfacets. And for the microfacets, we just assume that there is a preferential direction. That preferential direction is based off of the assumption that there are certain directions that are like shadowed by the microfacets. Like certain directions when light enters those directions, the light source will just be in shadow with regards to other microfacets. And then there's also occlusion happening, like when due to the spatial arrangement of the stochastically modeled microfacets, certain reflected directions are even occluded, like we're seeing it for the microfacet here. And therefore, we assume that that there is just a preferential direction with regards to those two vectors, and we assume that the direction where the contribution is highest is just the mean of the two, like the vector that is halfway between those two vectors. And there are like very simple BRDFs that are based on this idea, like the Blindfong BRDF, for example. But there are also more complicated microfacet models. But they usually assume that light has a preferential direction, and that preferential direction is based off of the microfacet distribution, and highest intensity is reflected into the halfway direction. So, and in practice, there's just a multitude of different BRDFs. The diffuse BRDF that we just discussed, that has an equal likelihood of reflection direction over the hemisphere above the light entry point, and a light contribution that is proportional to the angle between the light vector and the normal, and is actually view independent. Then we have those roughness models, which we'll colloquially refer to as specular rough models. Like they have this preferential direction, and that preferential direction basically has a margin of other directions that are also possibly taken, and that when we would sample this BRDF, like this conical shape here that I'm showing here, is like people colloquially refer to this as the specular lobe. Like inside that lobe, inside that cone, every directions are possible, and outside of that cone, directions will have no contribution. There is no light reflected into the direction with a probability greater than 0. And then we discussed those two models, and then there's just a multitude of other models. Like there are also idealized models that don't happen in nature, like perfectly specular models, which just have a single direction. And I will sometimes refer to those as so-called delta BRDFs, because underlying this is a delta distribution. And what we also see very often is just a combination of those different BRDF types, like a surface that is like 30% diffuse and 70% roughly specular. And then we just have a linear combination of the two, and the two BRDFs, and that just constitutes the possible light directions and the respective light intensities. If we were to evaluate that in a physically correct renderer, then we would have to evaluate that per wavelength. Like for every wavelength, we would potentially have different probabilities of reflection and also potentially different properties in general. And in such a setting, we would actually have to evaluate that for each and every wavelength. We will, during this lecture, mostly assume that we are approximating those BRDFs. And what people do in this case is they just evaluate this once and then multiply by the so-called material color, which is just an RGB material color. Like if you have, for instance, if you evaluate this diffuse model, then you will compute this dot product that we discussed earlier, and then clamp the dot product so that it's also always greater or equal than 0. And then when they compute that dot product, they will just multiply it by an RGB color. These RGB colors are actually the material colors that we discussed earlier. So quite often those RGB tuples that are associated with the materials in the material library and that are multiplied by the BRDF weight, sometimes they are just like global RGB tuples, like where you have a bunch of triangles, and all those triangles form a geometry, and the geometry has the same constant color. But sometimes, actually quite often, what people use in order to introduce more variation across the triangle is storing the material colors in what is called a texture image, and this is basically just a 2D raster image that is used to provide relatively coarse geometry with a bit of more detail. And the formats that are usually used for texture mapping, they usually build on a 2D raster image and then so-called texture coordinates. And those texture coordinates are used to look up so-called texels from the raster image and assign those texels to certain regions on the geometry. And let us have a quick look how that works actually. Yeah, and here's how this works. Just suppose we are given those two triangles with vertices v1, v2, v3, v4, and they share some of the vertices. And those vertices, they have an attribute, and we call those attributes like texture coordinates. And sometimes you'll also hear me refer to those texture coordinates as UVs or as UV coordinates. And what those texture coordinates are there for, they are coordinates of a coordinate system with respect to a given texture image. Like our material library tells us there's this texture image, and the texture image is associated with the triangle, and therefore we can use it by means of like the geometry ID of those two triangles. And in order to find out how to map the textures, like the texels from the texture, how to map them to our triangles, we have something that's called a texture coordinate. And the coordinate system that is induced by the texture image is this one here. Like we have the U direction, which is the horizontal direction, and we have the V direction, which is the vertical direction. And then we have associated with our vertices, we have those attributes, those UVs, or those texture coordinates, and they're just coordinates into this texture image. Like the geometry that I'm showing here is like kind of like a quad, right? And therefore I arbitrarily chose those texture coordinates that have their extreme points just where the coordinate system has its extreme points. This is kind of an arbitrary choice. Therefore, we know the texture coordinates that are associated with the vertices, and then we can find out, like for a certain position based on those texture coordinates, which texel to assign to, or which value from the texture to assign to the raster position. And therefore, what we do is first of all we have to interpolate those texture coordinates over the geometry. And in the case of triangles, people usually use barycentric coordinates for that. Like, matter of fact, for many, like for a quad, for example, or for polygons in general, people would use barycentric coordinates for that. And we'll discuss barycentric coordinates a little bit in the exercises. They are just the coordinate system with respect to the barycenter of the surface. And barycentric coordinates are actually not a necessity. Like, for example, when say our surface was a sphere, then we might instead use polar coordinates. So the first thing is that we determine a coordinate that's associated with the raster point that is with respect to the manifold defined by the surface. Right, and based on that coordinate, we then interpolate the texture coordinates of the surface that we're currently in. Right, like we'll take those three texture coordinates, the texture coordinate associated with V1, and with V2, and with V4, and then we use those barycentric coordinates or surface coordinates to interpolate the UVs over the triangle. Right. And we might then find out that the UV, with respect to the three given texture coordinates, is 0.3 in the U direction and also 0.3 in the V direction, right? And we only use that to perform a lookup in the texture. And then in general, we will find that the texture coordinates don't directly map to a texel, but they fall somewhere in between. Like there's like a choice that we have to make, and then we again use interpolation. Like people often use bilinear interpolation here, and you can also it's also possible to use a different interpolant. Like box filters are quite common, and people also use cubic filters. Then I use some type of interpolation, and based on the interpolation, you determine the value of the texel as a weighted average of its neighbors, right? Just like you would perform interpolation, right? And then with that, you know the actual color for the raster position that you are currently running. So in here you can see the whole thing again on a slide. Like we have our barycentric coordinates B1, B2, and then we use those barycentric coordinates B1 and B2 to interpolate the texture coordinates, like the texture coordinate that is associated with the red and the green corner in this case, and the texture coordinate that is associated with the red and the blue corner, and with the green and the blue corner. And this gives us a UV coordinate that we can use to index into the texture. And then we again use bilinear interpolation. Like in this case, we find out 4 neighbors that we have to interpolate over. And linear interpolation gives us a weighted average of those neighbors, and this is the texture color that we assign to the raster position. And here's a slide where you can see this whole thing in action. Like this is just a mere diffuse rendering with a constant gray assigned for the diffuse albedo, for the diffuse reflective property. Then here you can see a texture map that has much more fidelity and much more variety. And here are the UV coordinates for the 3D model, like the UV coordinates that the artist assigned when he created this 3D model. They created the 3D model with their 3D modeling software, and then assigned UV coordinates to the triangle. And this is the final outcome when you use those textures and apply them to the actual geometry. And as a matter of fact, textures cannot only store RGB tuples, but it's actually possible to store normal directions or normal vectors as tuples in a texture, and then during rendering, when looking up the shading normals for our geometry, have those shading normals not be interpolated but come from a texture, right? And what this helps with is normal mapping can help with the illusion that a surface is much more faceted than it actually is, right? Like take for instance this geometry here, and the geometry is comprised of a single flat surface, like a quad or a single triangle, and then we have this surface that is defined over the actual surface, and the actual surface is much more complicated, and the geometry that we store actually is much more coarse and has far less memory overhead, right? And in order to still store the fidelity of the original surface, we just store the normals in a texture, and then when rendering the flat surface, we look up those normals that are associated with the more faceted surface. We look the normals up and then use those for our shading calculations and for our lighting calculations instead of just the geometry normal of the flat surface. And the illusion that this creates is actually quite convincing when you're not watching very closely. Like, for instance, here's a pair of diffuse albedo map and normal map, and I applied both of those maps to this face of the cube here, and with those normal maps applied, the surface looks much more detailed than it actually is. A few remarks regarding the way that we handle surface geometry are in order. Like, the different methods that we reviewed so far, they cover a whole spectrum. Like, we have macroscopic versus mesoscopic versus microscopic methods. And what I mean by that is that on a microscopic level, we have triangles and actual geometry that describes our surface on a microscopic level, usually actually quite coarse. And then on a mesoscopic level, we have normal maps where the actual surface detail still manifests as objects. Yeah? Like when we have like certain details that actually manifests as high variance in the normal map, right? And then on the microscopic level, finally, we have our microfacet BRDFs that represent features that are just way too small so that we can actually devote any actual geometry or even normals to them. Like, and therefore, we just model them stochastically. So, and all that said, when we're striving for real-time rendering performance, the usual premise is low poly count. So what we try to achieve is to have relatively few actual geometry, and we try to get as much detail as possible from the textures and try to represent as much detail as we can, not on the macroscopic level, but on the mesoscopic, or if possible, even on the microscopic level. So this has several reasons. Like, on the one hand, we're interested in real-time performance, and therefore we strive for low poly count. But this also has to do with, and we will discuss sampling later, has to do with aliasing. When we have very fine detail, and those very fine geometric details, like hundreds or thousands of triangles, map on like only a couple of image pixels, then we get all sorts of aliasing effects. Then, for example, under movement, our renderings, for instance, are not stable because it's not fully clear which detail to map to what pixel, right? One more thing that is worth noting is that traditionally, physically based renderers, like renderers that are usually based for offline rendering, differ quite a bit from real-time renderers. Like, in a real-time renderer, traditionally what you would have is like a single texture, and that texture would just represent the different textures for diffuse, specular, and then you also have textures that encode roughness, like where you have a scalar that will just tell you for the surface patch how rough the actual surface patch is. And then you would have maybe normal maps, you would have extra maps for all sorts of parameters to the physically based BRDFs. And something that we can observe today is actually that those physically based rendering concepts are more and more adopted by the real-time rendering industry. And that has several reasons. One of those reasons is the aforementioned fact that when GPUs become more faster and when we have more cores available, then there's more compute power, and we have this thing with the fixed frame rates, and the real-time rendering people then might decide to just increase realism by adding physically based effects to their real-time renders. This is something that we can definitely observe. But another thing that made physically based rendering concepts so popular in recent years is the fact that they are much easier to author. Like for an artist, it is much easier to fine-tune and find parameters for a physical BRDF than it is for BRDFs, like for example the specular Phong BRDF. Reasons for that being that most physical quantities adhere to conservation laws, and therefore they are quite often normalized. And this quite often means that when artists have to adapt certain parameters, those are quite often parameters in between 0 and 1, right? While when you, for instance, have a specular exponent like the classical Phong reflectance model defines it, this is an unbounded value. So physically based rendering in general becomes more and more popular, and with physically based rendering we usually have all sorts of textures that store all that surface detail that is associated with our geometry. And with that we have a fair understanding of how fragments are created, like those entities that are almost pixels but they are not yet pixels. And we saw how those fragments are created using scan conversion methods, and we also have a basic understanding of how to obtain colors for our fragments. Like we know that both surface properties as well as the properties of the light sources in the scene determine the actual colors of our fragments. So, and then finally, when we construct our images, we have to finally determine which fragments contribute and which fragments don't contribute. And with the GPU-based algorithms that we're going to discuss, like the current discussion is pretty much focused on the rasterization algorithm. And this here is irrelevant for algorithms like ray tracing, but on a GPU, what we have is a data structure that is called the depth buffer or the Z buffer. And using that data structure, we can perform a visibility test, like the depth test. And the data structure is basically just a image-sized or screen-sized two-dimensional array. And that two-dimensional array just stores the depth value of the closest fragment that was encountered so far. Like when we, to begin with, we initialize the depth buffer with something that tells us that there aren't any fragments so far, like with infinity or something like that. And then when our raster engines start producing fragments, we blend and we write those fragments into the depth buffer. And assuming that we only have opaque geometry, then we just use our raster engines to determine the raster positions. And then we also interpolate depth, so the z value over the primitives, over the triangles. And then we know for each fragment, we know its depth. And when we encounter, when we have a fragment, and then we encounter that at the same raster position there is another fragment, then the fragment wins, so to say, whose depth value is smaller, right? So this data structure, the Z-buffer, allows for very simple visibility tests for fragments. Again, and when we use alpha blending, like when we allow for semi-transparent primitives, then the fragments also may also be semi-transparent. Like then they have an RGB color associated with them, and the alpha value, determines how transparent the fragment actually is, and then the final pixel color is actually a linear combination of several fragment colors, right? Like as it's indicated here on this in this illustration, like you have several fragments that are blended on top of other fragments, like and then the blended color determines the actual color of the pixel that is written to the screen. So, and if we have semi-transparent geometry, then what is important to note is that order matters. like in the case of the fully opaque geometry, it doesn't really matter in which order the fragments occur, right? Whenever a fragment occurs that is closer than the fragment that is already written in the frame buffer, then we just overwrite the current entry in the frame buffer and are good. Again, when we're dealing with semi-transparent geometry, we have to make sure that the order in which we blend the fragments is actually the visibility order. Yeah? Like because the operator that we're using for alpha blending, the so-called over operator, is a non-commuting operator. So there are actually a bunch of approaches that people use. So the very simplest approach is just to sort all the geometry. Whenever we remove the camera, just sort the whole geometry. Like there are some corner cases with certain types of overlap that can even be handled by that. And then you maybe even have to tessellate your geometry to resolve those corner cases. But approaches like this, where you sort the geometry, are actually the simplest approaches. And like as a matter of fact, what people usually do is they don't sort the whole geometry, but they they create like what people sometimes call bins. Like they have a transparent bin and a bin for the opaque geometry, and then first bin the whole geometry into the two bins based on their class of geometry, and then they start by filling the frame buffer or the depth buffer with the opaque geometry, and then there are some values in the depth buffer. So just suppose this is our depth buffer, our frame buffer, and the order of the fragments is the closest fragment is here to the left, and then to the right the fragments, the depth values get bigger and bigger. So, and then just suppose that we initially render all the opaque geometry into the frame buffer, and so we have a fragment here. So that means that whichever semi-transparent fragments occur behind that fragment, that opaque fragment, are invisible anyway. Yeah? So their handling doesn't even matter, and maybe the GPU can even optimize that and might see that the fragments are hidden and won't perform any blending operations for them. And then, like when we blend our fragments over the opaque geometry, the only fragments that really matters are the ones that are in front of the opaque geometry, and therefore it is a common optimization that people don't sort all the geometry, but that they start with the opaque geometry, and then the frame buffer is already filled, and the opaque geometry doesn't need any sorting. And then there's special handling for the semi-transparent geometry. Like when there is only very little semi-transparent geometry, this is viable. Like when there are only few triangles that are actually semi-transparent. But if there's a bunch of them, then sorting might actually become quite. So and there are actually other more advanced techniques, like for instance dual depth peeling or using per pixel linked lists. So in order to support semi-transparent geometry in renders, if sorting all the geometry is just not an option. Another thing that is worth noting is that blending of fragments usually happens in hardware. Like we will discuss this later in the architecture sessions when we're talking about GPU architectures, that there's this unit called the ROP, which is basically a retirement unit for fragments. And this unit usually performs blending in hardware. And there's certain ways that blending can be performed, and GPUs usually allow us to configure this. And the typical function that is used for alpha blending is the over operator that is depicted here. And there's also other ways that can be used to blend colors, like depending on the order, like we might not blend them in front to back order, but in back to front order, then the equation becomes a bit different, or we might actually use other ways of blending the fragments. But this operation is usually supported in hardware when we use the rasterization algorithm on the GPU. Like, and then finally, like so far, we were only concerned with objects, like with three-dimensional primitives, and those three-dimensional primitives were scan converted into fragments, and then we wrote single fragments into single slots that represented pixels, right? So now you can imagine we have to take care of what happens when we write those fragments to the depth buffer, and at which point we actually want to display the depth in the frame buffer. Right, like when we're doing this in an unsynchronized fashion, then what happens is that we might actually display an incomplete frame buffer and depth buffer. This is, of course, undesirable. And therefore, the GPUs implement something that is called double buffering. And sometimes they even support things like triple buffering, where you have a so-called front and a back buffer. Like you have two buffers, and you use the so-called back buffer as the scratch area where you construct your image in. And this is just a hardware side buffer resides in some memory region that is dedicated to that. And the per fragment operations, blending, depth test, and so forth are performed in the back buffer, and the back buffer is invisible. So, and then at some point, our application might decide that we should display an image because it's fully constructed, and then the application just swaps the two buffers. And this is usually done by swapping two pointers. This doesn't imply any memory copies, but the two buffers just switch roles. And this usually has to happen synchronously with the display controller. So whenever the display controller displays something, we have to make sure that the front buffer is filled with fully assembled images in a synchronous fashion. And this basically allows us to render without flickering, right? Because otherwise, if you were to render directly to the buffer that the display controller reads from, then you would see how the image is actually constructed, so how the depth buffer is actually filled. And therefore, we use this technique that is called double buffering. So tomorrow, we'll have a brief intermezzo on sampling and on anti-aliasing, as this is actually a pretty important technique for 3D rendering, and is also important to our later discussions. And then we will finally go over to discuss the three algorithms that I already teased in the first computer graphics lecture, and then we'll finally look into parallel rendering algorithms in one of the later sessions. And I hope to see you then.